This is the last video for Chapter 10, dealing with acids and bases. This last section talks about buffers. I believe this is 10.6. Buffers are a very important component to systems. They are solutions that are going to resist pH changes. And they're very important to us, especially you'll see these buffers come up in biology. Okay, yes, chemistry and biology can cross over. And they're very important because pH is something that has to be regulated in systems such as our body. Okay? So let's write down our definition of buffers. Fairly simple, straightforward definition is that these are solutions that resist change in pH. Now there's a specific way for us to prepare a buffer. And that we can't just throw chemicals together and call it good. We have to have a very specific set of chemicals, in that we want to combine a weak acid and its conjugate base. So we have an acid and a base being combined, but they have to be related so that a neutralization reaction doesn't occur. Okay, and the key to having a weak acid versus a strong acid is we are going to utilize that equilibrium. So weak puts us in an equilibrium, and that allows us to be able to shift from our reactants to our products, or our products to our reactants, and that's part of how our solution is going to resist the change in pH. So if we look at an example, let's look at a vinegar buffer. Right, buffer prepared from vinegar. Our chemical name for vinegar is acetic acid. So we have a weak acid. Our weak acid is our acetic acid, so HC2H3O2. And then we need its conjugate base, right? So the conjugate base of acetic acid. And to review conjugate bases, maybe look at the first videos for Chapter 10. The conjugate base is the result of our acid donating a proton. So we'd be left with C2H3O2 minus. That's the acetate ion. So if we combine these two chemicals, two solutions with those in that, we will prepare a buffer. Now the thing to remember, or a trick that usually trips up students, is we can't just go and find a solution of the acetate ion. Okay, we learned in Chapter 8 with equivalence that our total charge in a solution has to be neutral. And that was the whole point of the equivalence. Our positive equivalents have to match the negative equivalents so that solutions are neutral. Okay, we can't have a charged solution. It doesn't work. So we can't actually find this acetate ion solution. So how we're going to prepare this is we need to add a solution that's going to contain the acetate ion, but it's also going to have some sort of cation paired up with it, but we want a cation that's going to be soluble. Okay, soluble meaning that it's going to break apart. So we want a solution that's going to have this acetate ion, and then we also, because of the rules of equivalence, we're going to have a matching cation. Okay, so we basically need to pair this up with a cation that's always going to be soluble. Looking back to our solubility rules, well, my note of reminding you is that we have potassium ion, sodium ion, and the nitrate ion are always soluble. Okay, so when we're preparing buffers, in order to get our conjugate base, we're usually going to take the salt of that conjugate base paired with either the sodium ion or the potassium ion. Okay, or we can choose anything else that's going to be soluble, but typically these are the most common that are chosen. Okay, so in order to get a solution of our base, or our conjugate base here, is we are going to add the salt of the conjugate base. Okay, in this case, we'll say add a sodium acetate. All right. So the overall equation of what we're looking at when we have this vinegar buffer, okay, remember I said that we had the weak acid because we want to utilize this concept of the equilibrium. Okay, so we're going to prepare our buffer from the acetic acid and from our acetate ion. Okay, we're going to get that from our sodium acetate because this is going to completely dissociate between sodium ion and C2H3O2 minus. Okay, and because this is a strong electrolyte, okay, that sodium ion completely dissociates. Now the sodium ion is always going to be in that solution, but we kind of just ignore it. We call it a spectator ion because it's there. It has to be in order to balance that charge, but it's not actually participating in the chemical equation. Okay. So for now, we're basically going to just ignore that. So we want to look at our equilibrium of our acetic acid. So we have HC2H3O2, and because this is an acid, we have water present, and this is a weak acid, so we're in equilibrium with H3O plus and our acetate ion. This is our chemical equation of what's happening with our buffer. Okay, and basically what we have is we have added two solutions together. One solution provides a high concentration of our acid. The other solution provides a high concentration of our conjugate base. Okay, so we have our equilibrium established, and we have a lot of chemical to work with over here, and we have a lot of chemical to work with over here. So the whole point of our buffer is we want a solution that's going to resist a change in pH. Now recall from section 10.4, our pH is dependent upon the concentration of H3O plus. So our pH is dependent on what this concentration is. So what I'd like to do is kind of discuss how this buffer works. Okay, why does our pH not change? In other words, why does pH not change? Well, what we have to keep in mind is pH is dependent on the concentration of H3O plus, right? So pH is equal to the negative log of the concentration of H3O plus. So if we are going to change the pH, that means the concentration of H3O plus is going to change. If, in the case of this buffer, we don't want the pH to change, that means that the concentration of H3O plus does not change. So that means that if we add an acid or a base to this buffer, we have to somehow kind of absorb that acid or absorb that base without changing our concentration of H3O plus. So let's look at what happens if we add an acid. And it doesn't matter what acid we add. Okay, let's just say we're just going to add H+. Very generic acid. Don't get too specific. Okay, we're going to add H+. What happens is opposites attract. Our H+ is going to want to combine with our acetate or acetic, our acetate ion, right? Positive, negative. Okay, so if we add acid, we're going to have H plus C2H3O2 minus, right? So we're just going to add to this side, which is going to form HC2H3O2, right? So if we add acid, we're just going to form more of this. So if we add acid, we're going to take some of this, we're going to form that. What happened to the concentration of H3O plus? Did we change it? Well, we didn't change it. Okay, the acid that we added interacts with this to form more of that. Okay, as long as we have both of these present, they can do that. They can switch back and forth. That's fine. They can switch back and forth all day for however much of this acid that we add. It's going to combine with that. It's going to form that. We don't change that. Okay, so what happened to the concentration of H3O plus? It stays the same. Right? If it stays the same, that means that the pH stays the same. All right, let's look at if we add a base. And we're just going to think of this very generically, OH minus. Acids are attracted to bases, so our base is going to interact with our acid. So we're going to have HC2H3O2 plus our base is going to form water and our acetate ion. So if we add base, it's going to interact with our acid. We're going to form more water and more of our acetate ion. So again, the key question is what happened to the concentration of H3O plus? Again, it stays the same, and if it stays the same, then our pH does not change. That's how a buffer works. As long as we have a lot of our acid and a lot of our conjugate base, okay, we can add acid and we can add base. It's always going to affect those concentrations, but not the concentration of H3O plus. So if we're not affecting the concentration of H3O plus, our pH does not change. All right. So let's work through an example of something that is a test-like question for you. So let's look at a number of solutions, 2 solutions here, and see if they will form a buffer. All right. So in order to prepare a buffer, we have to have 2 conditions that are met. 1, we have to have a weak acid. Okay, so going back up here to our definition, how to prepare a buffer, we have to have a weak acid, okay, or a weak base. Okay, we can have the opposite buffers. If we have a weak acid, we also have to have its conjugate base, which is usually going to be in the form of the salt of the conjugate base. Okay. If you combine a weak base, then you'd have its conjugate acid. Okay, so we'd have that acid-base combo happening. Okay. Now, in section 10.2 is where we discussed strengths of acids, strong versus weak. And remember I said you don't have to memorize that. Okay. So that would be something that would be given to you. So in addition to, say, these combos, I would also tell you that sodium hydroxide, well, it's a strong base. I'll put that in blue. Sodium hydroxide is a strong base. HCl is our acid, and it is strong. H2CO3, this is an acid, and it is weak. Hydrogen fluoride, this is a weak acid. Hydrofluoric acid. And HCl, this is a strong acid again. So, our first one here, we have a strong base and a strong acid. So is this a buffer? Well, we don't have either conditions met. We don't have a weak acid or a weak base, and we don't have a conjugate acid or a conjugate base. So this is not a buffer. Next question, we do have a weak acid, so our first condition is met for our buffer. So what we want to determine is if we've added our salt of our conjugate base here. So our conjugate base of H2CO3, that's going to be the result from losing one of the protons. So our conjugate base is HCO3 minus. We have to look at this here to see if that is going to produce the salt of our conjugate base, or if this is the salt of our conjugate base. So this would break apart into K plus and HCO3 minus. Okay, looking at your solubility rules for that. So we do have, in fact, our conjugate base from our second component. So this is, yes, a buffer. Our third example here, we have HF. This is a weak acid. Okay, so again, we need to see if we have the conjugate base, the salt of our conjugate base. Our conjugate base of HF is going to be F minus. Okay, NaCl is going to produce Na plus and Cl minus. neither of which is our conjugate base here, so this is not a buffer. Our last example here, okay, it's tempting to look at this and say, well, from HCl, I'm going to get the chloride ion. From NaCl, we have Na plus and Cl minus, so I get the salt of my conjugate base. Okay, that's one component of the buffer, but the other component is that we have to have a weak acid. HCl is not a weak acid, it's a strong one, so this is not a buffer. So work through some Q and P's with that. Look at your sapling sites to be able to identify what is a buffer and what is not. Definitely going to see a question like this on your exam.